Okay, so hi everybody, welcome back. What we're doing today is wrapping up our chapter 16 lecture on sound, and by the end of this video we'll be completely done with all the content from chapter 16 that I wanted to cover. Where we left off last time was an introduction to this idea of constructive and destructive interference. So I want to take that a step further and talk about interference in space. So here's the scenario. Let's say we have two sources of sound waves. So you can imagine there's a speaker here, number one, and a different speaker here, number two. And they're both emitting sound waves that have the same exact frequency, F. Now, there's going to be an observer, someone who's listening to the sounds emitted by these two different sources. Depending on where that observer is located, that observer might be at a point of constructive interference or at a point of destructive interference. So here's how this works. The two sources are going to be in phase. And that means at the moment when source number one is emitting the crest of a wave, source number two is also emitting a crest of a wave, okay? But because the waves are going to have to travel different distances to get to the observer, so x1, the distance between the observer and speaker number one, and x2, the distance over here, may be different. That can result in a phase difference between the two waves that the observer is receiving. And remember, if delta phi, the phase difference between the two waves, is an even multiple of pi, so 2n times pi, where n is some integer, that will be a point of constructive interference. And then if delta phi is equal to 2n plus 1 times pi, so it's an odd multiple of pi, then we'll have destructive interference. So of course, in the case of constructive interference, that corresponds to a louder sound. And if you're standing at a point of destructive interference, the waves are canceling out, giving you a minimum in the intensity of the sound. So the way we're going to work this out to figure out where we have destructive and where we have constructive interference, well, remember that the observer is going to hear a superposition of the waves emitted by source 1 and 2. So here's how we'll write out the waves emitted by each source. So the displacement of the wave emitted by source number 1 is going to be given by a times sine of k x1 minus omega t. I'm using x1 here because, of course, the wave might have to travel a different distance compared to wave number 2. So for wave number 2, the displacement is given by a times sine of k x2 minus omega t. Again, we want to keep x1 and x2 distinct from one another. So here, x1 and x2 are the distances traveled by each wave from the source to the observer. So delta x, therefore, is going to be the difference between those two distances, x2 minus x1 absolute value, to make sure it comes out positive. This is going to be called the path length difference. Okay, so with all that set up for us, let's work out the conditions that have to be met in order to have constructive interference and destructive interference. Okay, so here's what we have. D1, the displacement of wave number 1, is a function of x1 and t. That's going to be a times sine of k times x1 minus omega t. And then, of course, wave number 2 is going to be a times sine kx2 minus omega t. Okay, the phase difference between the two waves is something we want to account for. And remember, the phase of a wave is just what's inside of the sine function. So this would be phi 1, kx1 minus omega t. And this would be phi 2, kx2 minus omega t. So the phase difference between the waves. Delta phi is going to be phi 2 minus phi 1, absolute value. So we have delta phi equals, phi 2 is kx2 minus omega t. and subtract from that phi 1, which is kx1 minus omega t. So first of all, omega t cancels here and here. And then we just have kx2 minus kx1. K is a constant which can be pulled out. And then we have x2 minus x1, absolute value. Okay, first thing to note is the path length difference. Delta x is defined as x2 minus x1, absolute value. So that's this term right here. That's the path length difference. And the wave number k is equal to 2 pi divided by lambda. So let's make those two substitutions for k and for x2 minus x1. So we have 2 pi divided by lambda times delta x. That's the phase difference between the two waves right there. And of course, what we can do then is apply the constructive interference condition. So if the waves are going to interfere constructively, then what has to be true is the phase difference delta phi is going to be 2 pi times n, where n is 0, 1, 2, or any integer. Remember, that's the condition we worked out in the last video. So what I'll do is I'll put 2 pi over lambda times delta x in for delta phi, and then I have 2 pi times n on the other side of the equation. 2 pi cancels. Also, I can flip things around to say that delta x is equal to n times lambda. So for constructive interference, what we have is the path length difference is an integer multiple of the wavelength. So as long as that's true, you have a point of constructive interference. Now, on the other hand, for destructive interference, the condition is delta phi equals 2n plus 1 times pi, again, where n can be 0, 1, 2, or whatever. And again, delta phi is 2 pi over lambda times delta x. We're setting that equal to 2n plus 1 times pi. So first, let's cancel out pi. And then let's multiply by lambda on both sides. And then let's divide through by 2. So get rid of the 2 here. This gives us delta x is equal to n plus a half times lambda, again, n is equal to 0, 1, 2, and so on. This is telling us that the path length difference is equal to a half integer multiple of the wavelength in order to get destructive interference. Okay, so those are the conditions. Okay, so what we found is in order to get constructive interference and get the highest possible intensity of the sound, delta x is going to be n times lambda, where n is equal to 0, 1, 2, 3, or any integer. So this is telling us that the path length difference delta x, again, is some integer times lambda, some integer multiple of the wavelength. On the other hand, for destructive interference, we have delta x is equal to n plus a half times lambda, for n is equal to 0, 1, 2, 3, and so on. This is telling us that for destructive interference, the path length difference, delta x, is a half integer multiple of the wavelength. So that's what we found. So let's use that idea in this problem here. Let's say we have two speakers emitting sound waves with a frequency of 256 hertz. The two speakers are in phase with each other. And the speakers are separated by a distance d is equal to 3.50 meters. So we have an observer standing over here against the wall along the center line of the two speakers. So there's the center line of the two speakers. So the distance, by the way, to the wall, L, is equal to 4.5 meters. So the question is, do the waves interfere constructively or destructively at the point where this observer is standing? So pause the video, try to work this out, see what you get, and then come back to it when you think you have your answer. Okay, so in this case, x1 is the same as x2, meaning the waves from each speaker have to travel the same distance to get to the observer. So therefore, the path length difference for the two waves, x2 minus x1, is equal to 0. So in other words, delta x divided by lambda is equal to 0. Now, which condition does that meet? Well, this meets the constructive interference condition. Because remember, delta x is equal to n times lambda for n is equal to 0, 1, 2, or 3. So we're just at the n equals 0 point of constructive interference in this case. Okay, let's take a look at another example. So same basic setup. We have these two speakers emitting sound waves with a frequency of 256 hertz. The speakers are in phase, and they're separated by a distance d is equal to 3.5 meters. We have an observer standing along a wall, which is a distance L equals 4.5 meters away along the center line of the two speakers. But what happens is the observer is going to start walking along the wall this way, okay? So the question is, how far along the wall is the observer going to have to move? So what is this distance S, such that they are at a point of destructive interference? So we know if they're right here at the center line, they're at a point of constructive interference. But if they move this way for some amount, they're going to be at a point of destructive interference. So the question is, what is that distance they have to move to be at a point of destructive interference? So let's work it out. Okay, so remember that when it comes to destructive interference, we have delta x equals n plus 1/2 times lambda, where n is equal to 0, 1, 2, or any integer beyond that. And let's also remember that v is equal to lambda times f. Why is this going to be useful? Because lambda is not something we currently know, but we can easily solve for it by just saying lambda is equal to v over f. And then therefore the wavelength of the sound waves we're talking about here is 343 meters per second. That's v, the speed of sound, divided by the frequency, which is 256 hertz. And remember, hertz is the same as inverse seconds. So unit-wise, we're left with meters. 1.3398 with 3 sig figs meters is the wavelength. Okay, so how are we actually going to apply this idea to our current situation? Well, remember the path length difference, delta x, is equal to x2 minus x1, absolute value. So now we have to draw a little picture to figure out what the path length difference is going to be. in this case. So we have two speakers, speaker number one, speaker number two. So I'll call this S1 on the bottom, S2 on the top. The distance between them is D. Then we have the center line of the two speakers right there, which is a distance L away. So in other words, the wall that the person is walking along is a distance L away from the two speakers. And the distance the person is going to walk along that wall is S. So there's S, and that takes us to where the observer is. Okay? So X1 is the distance between the first speaker and the observer. That's X1 right there. X2 is between the second speaker and the observer. So there's X2 right there. So out of this picture, we can construct two triangles. One of them looks like this. We have distance L as this horizontal side. Then this vertical side is going to be D over 2 plus S. And then the hypotenuse is going to be X1. So there's one right triangle we can pick out of the diagram. And then we have another one where this side is L, this horizontal side, and then going down this vertical side is D over 2 minus S to get where the observer is. And then the long side, the hypotenuse, would be X2. Again, that's a right triangle. So in this case, X1 just happens to be bigger than X2. So the difference, if we want to make this a positive number, would be X1 minus X2. Okay, so now what's the formula for the path length difference? Well, based on our pictures, delta X, which is X1 minus X2, is going to be, well, X1 will square root D over 2 plus S squared plus L squared. That's just the Pythagorean theorem to get X1. Then I have to subtract X2, which is just another application of the Pythagorean theorem, but now we have D over 2 minus S squared plus L squared. So that's what we have for the path length difference. So what we're going to do with that, again, is apply the destructive interference condition, which again is n plus a half times lambda. So this formula for delta x should equal n plus a half times lambda if we want destructive interference. Okay, so here's what we have. Square root d over 2 plus s quantity squared plus L squared minus the square root of d over 2 minus s quantity squared plus L squared equaling n plus a half times lambda. But let's set n equal to 0 for the first point of destructive interference. So remember, the smallest value of n is 0, so this would just be a half times lambda. Now let's take an account of what we have here. D, the distance between the two speakers, is 3.50 meters. L is equal to 4.50 meters, and then lambda, as we just found, is equal to 1.3398 meters, and we'll keep 3 sig figs on that. What we don't know is S. We're trying to figure that out. So this equation, which I'll put in a box, is enough to solve for s, because s is the only unknown variable in that equation. However, the algebra gets a little bit ugly. So I worked out in my notes that you can see on Canvas exactly how to solve this algebraically, but I don't think it's worth our time here on the video. So check out my handwritten notes if you want to see exactly how to solve that equation algebraically. But here I'm just going to skip to the answer. So if we solve this equation algebraically, using the given values, we're going to find s is equal to 0.939 meters. Okay, so that's how you do this. Okay, so as a follow-up to that one, let's take a look at this question. We have the same exact physical setup as before. We have our two speakers, speaker 1, speaker 2, each emitting a sound wave with the frequency of 256 hertz. They're separated by a distance d equals 3.50 meters. We have an observer standing against a wall that's a distance L equals 4.5 meters away from the speakers. And this observer is going to move off the center line of the two speakers this way, a distance s equals 1.98 meters. So when the observer is standing here, the question is, are the waves going to interfere constructively or destructively at the location of the observer? So pause the video, try to figure this out, and come back to it when you think you have your answer. Okay, so for this one, I'm going to use some of the work that we developed before in the previous example. The path length difference for these two waves, delta x, remember, is given by the square root of d over 2 plus s squared plus L squared minus the square root of d over 2 minus s squared plus L squared. So here we can actually just plug in all these numbers to get the path length difference. So here we have the square root. Now d is 3.50 meters. Divide that by 2 plus s, which is 1.98 meters. Square that plus L squared. So that's 4.5 meters squared here. Then subtract square root. We have d over 2, so that's 3.50 meters over 2. Now minus s, so minus 1.98 meters, square that, and then add 4.50 meters, square that as well. Okay, so what's the path length difference in this case? It's going to be 1.339 meters. And if we keep 3 sig figs, about 1.34 meters. Okay, well, another thing we have from before is we calculated the wavelength of the sound waves, which was 1.3398 meters, and that can be rounded to 1.34 meters. Okay, so immediately we notice that delta x is equal to 1 times lambda. In other words, the path length difference is a whole number times the wavelength. So it's an integer multiple of the wavelength. It follows the constructive interference condition that delta x is equal to n times lambda for n equals 0, 1, 2, and so on. So what we're dealing with here is constructive interference. Okay, so next, let's talk about interference in time. Let me explain what I mean by this. Let's consider two sources that emit sound waves that have slightly different frequencies, F1 and F2. So you can imagine we have two speakers. One of them is playing a sound with a frequency F1. The other is playing a sound with a frequency F2. So if you're an observer and you're standing at a fixed position, so you're not going to move around to different positions like before, you're just going to stand in a fixed position, what are you going to hear? Well, sometimes those two waves are going to constructively interfere, but at other times they're going to destructively interfere. So the overall effect of hearing those two waves combined is that you are going to hear beats. So these are what we call the periodic variations in the sound intensity. In other words, the sound intensity is rising and falling in a rhythmic way. That's what we call beats. So for this, it's better just to show you an example of this using a guitar so you can actually hear what it sounds like when we create beats with two slightly different frequencies being played at the same time. Okay, so to give you a better sense about what we mean by beats, I'm going to play two notes and then... And so the second one has a slightly lower frequency because I tuned the string down a little bit. So when I play them together, that would be a case where we have two sources of sound with two slightly different frequencies. And here's what it sounds like when we do that. So what I want you to listen for is that periodic rising and falling of the sound intensity. It kind of sounds like da 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 da, that kind of thing. Those are the beats. So here, listen for it again. And that's what happens when you play two slightly different frequencies at the same time. So actually, when you're tuning a guitar, you're actually turning the knob and waiting for those beats to go away. Because as soon as the two notes have the same frequency, then those beats go away. And now this is what it sounds like. Okay, in case that was difficult to hear using the guitar, I'm going to show you another example. I'm going to generate two sound waves using my computer, one with a frequency of 450 hertz and the other one with a frequency of 455 hertz. So two slightly different frequencies played at the same time sounds like this. And listen for those beats. Now, what if I change the frequencies slightly? Let's say I play 450 hertz at the same time as 452. So I'm going to make the two frequencies a little closer together than before. Here's what it sounds like. So notice now the beats are happening more slowly. That's what's going to happen when the two frequencies get closer together. And when the frequencies are exactly the same, then those beats go away altogether. Okay, so when it comes to the mathematics behind beats, we have two different waves, but each wave has the form d of x in t is equal to a times sine of kx minus or plus omega t. Right? So remember, omega, that's equal to 2 pi times f. And how about, since we're dealing with a fixed position, just to make the math a little easier, we're going to set x equal to 0. Okay, it really doesn't matter what you set x equal to, but just some fixed position. Okay, so therefore, we have a times sine of just omega t, and omega t is going to be 2 pi f times t, again at a fixed position. And since we have two different waves, we want to find the sum of two waves that have this general form. So we want d total, which is d1 plus d2. So d total as a function of time now. It's going to be equal to a times sine of 2 pi times f1 times t. So that would be the first wave. And then we have a times sine 2 pi times f2. That's the other wave with a different frequency, f2, multiplied by time. And we want to add those two waves together. So a trig identity that I'm going to bring into play here is that if we add sine of one angle, theta 1, plus sine of another angle times, which is theta 2, okay, whatever those two angles might be, this is equal to 2 times cosine, difference between the angles theta 1 minus theta 2 over 2, and then sine of the sum of the two angles, theta 1 plus theta 2 over 2. So that's just a trig identity that we're going to use, because in this case, theta 1 is going to be 2 pi f1 times t. Theta 2 is going to be 2 pi f2 times t. So when we apply the trig identity, we have d total as a function of time. So we have the factor of 2 coming out to the front times a. And then we have cosine of, so I'm going to take theta 1 minus theta 2. Okay, so I have a 2 pi in there. And then I'm going to have f1 minus f2. And then we divide by 2 times t. And then that's going to multiply sine. So in this case, I'm going to add theta 1 and theta 2 and then divide that by 2. So I have 2 pi, that's common to both terms, f1 plus f2 divided by 2 times t. So this is one way I can write the expression for the total displacement of those two waves that have slightly different frequencies. Okay. So let's take a look at what we worked out as far as the mathematics of beats is concerned. So remember, at a fixed position, let's say x equals 0 for simplicity, we have d1, the displacement for wave number 1, equals a sine of 2 pi f1 times t. For d2, we found that it's a times sine of 2 pi f2 times t. And when we add those two waves together, the sum of d1 and d2 can be written this way, which is 2 times a times cosine of 2 pi f1 minus f2 over 2 times t. Then we multiply that by sine of 2 pi times f1 plus f2 divided by 2 times t. So the reason I'm writing it this way is that when we plot this out, if you actually plot this function out, this is what it looks like. You're going to notice that we have some very fast oscillations going on top of some very slow oscillations. And really that's what makes a beat, is where you have these really fast oscillations enveloped by these slower oscillations. So there are two different frequencies to think about. One of them is right here inside the cosine function, f1 minus f2 over 2. The other one is inside the sine function, which is f1 plus f2 over 2. Those are the two different frequencies we're dealing with in this graph. Now the higher frequency, that would be the faster oscillations you see in the graph, is actually the average of f1 and f2. Remember, the average of f1 and f2 would just be f1 plus f2 divided by 2. That's this one. And that's the frequency of the tone that you actually hear. So in other words, if I were to play like 180 hertz and 182 hertz at the same time, it would sound like the average of those two, 181 hertz, okay? Now, the lower frequency, which is this one here inside of the cosine function, that's f1 minus f2 divided by 2. Well, that's the frequency of the slower oscillations shown with this red curve here. So in other words, That's the frequency of the oscillation of the envelope of this overall red curve here. So what does that tell us about the beats? Remember, the beat frequency would be the frequency of the rising and falling of the sound intensity. So if you're at a maximum of sound intensity and then the sound intensity goes to 0 and then you go back to a maximum, that's 1 beat right there. So if we look at the envelope, the red curve, what we see on the graph is 1 period for this oscillation, right? Because we start at a maximum, we go down to 0, and then we go back to a maximum. But as far as the beats are concerned, this is actually showing 2 periods for the beats. Because right here, we're at a maximum in the sound intensity. Then we drop down to 0. And then here we go back up to a maximum in the sound intensity. So it's loud, quiet, loud, like this. So the point is, the beat frequency, the frequency of the rising and falling of the sound intensity, is double the frequency of this red envelope. So therefore, we're going to multiply by 2 and get rid of that factor of a half on the bottom. So the beat frequency is just F1 minus F2. And we'll put an absolute value around that just to ensure that this is a positive quantity. So that's the beat frequency. So let's do an example then. Let's say you have one guitar string that's tuned to a frequency of 256 hertz, and you have a second string that is tuned too low. So F2 is going to be something less than 256 hertz. Now, when you play those two strings together, they create beats with a frequency of 3 hertz. So what is the frequency of the out of tune string? What is the frequency F2? So pause the video, try to work this out using the formula for the beat frequency, then come back to the video when you have your answer. So again, the frequency of beats is given by a pretty simple formula. F beat is equal to the absolute value of F1 minus F2. And in this case, F1 is greater than F2. So we have F beat is equal to F1 minus F2, considering we're dealing with an absolute value. We want to know what F2 is. Well, that's just F1 minus F beat. We solve for it. So the frequency of the first string is 256 hertz. Subtract the beat frequency of 3 hertz. So the out of tune string, the one that's tuned too low, is at 253 hertz. So pretty simple to work with this formula for the beat frequency. Okay, so let's do another question. This one is a little bit more conceptual. Consider the two sound waves depicted in the graphs shown below. We have wave A and wave B. For each one of these, we're showing the displacement of the wave on this axis vertically and time on this axis horizontally. Each wave, A and B, can be thought of as a superposition of two waves with slightly different frequencies because, of course, both of these are showing beats. The question is, which one of these has the two component frequencies further apart? So again, wave A, you can think of this as a mix of two frequencies. Wave B, another mix of two frequencies. But in which case are the two component frequencies further apart? So pause the video, think about this, see if you can get your answer, and then we'll go through it together. Okay, so this one, we don't really need to make a calculation to figure out. We have the two graphs that we can just look at and determine the answer. So just by looking at the graphs, it should be pretty clear that wave A has a higher beat frequency. So in other words, the rising and falling in sound intensity is happening faster at a higher frequency for wave A compared to wave B. But remember that the beat frequency is just F1 minus F2. So the beat frequency is the difference between F1 and F2. So if wave A has a higher beat frequency, that means its component frequencies are further apart. So it's wave A that has component frequencies that are further apart compared to wave B. So that's the answer. All right, so the last thing we're going to talk about as it pertains to sound is the Doppler effect. So we're going to spend the rest of this video on the Doppler effect. Okay, so the Doppler effect is something that you've probably experienced at some point in your life. Let me outline a scenario for you. So let's say you're standing on the side of the road and there's a fire engine coming by, driving towards you. And while it's driving towards you, the siren is going, so it's emitting a sound. And then the fire engine passes by you, so now it's moving away from you, and you're still hearing the sound that the siren is making, but it changes. Okay, so when the fire engine is coming towards you, it sounds higher pitched, and when it's moving away from you, after it's passed by you, now it sounds a little bit lower pitched. That's the Doppler effect, okay? So the Doppler effect in general is a shift in the apparent frequency of the sound wave due to the motion of the source and or the observer relative to the air. So the idea here is we have something that's emitting sound, that's the source, and then we have someone who is listening to that sound, an observer. And if there's motion of either one of those, either the source or the observer relative to the air, then the frequency of the sound is going to be shifted by some amount. So we know the intuition for this from the fire engine example. If the source of sound is moving towards you, then you hear a higher frequency than before. And if the source of sound is moving away from you, then you hear a lower frequency than before. Now, the notation that we're going to use when it comes to the Doppler effect is this. Anytime you see a prime on something, like F prime, that would be what the observer hears. Okay, so F prime is the frequency heard by the observer. And then F without the prime is referring to the source. So what is the frequency just emitted by the source? Now, whenever we refer to a speed in our formulas, it's always going to be measured relative to the air. So that's another important thing to remember. All speeds are relative to the air. Okay, so next we're going to derive the Doppler shift. And we're going to do this in a couple different steps. So first, what I want us to think about is two different cases. In the first case, shown over here, we have a source of sound waves and an observer, and they're both stationary. So neither one of them is moving relative to the air. Now, in this second case, we have an observer who is stationary, but a source that is moving towards the observer. So these two cases are going to look slightly different. Let's take a look at the first case. Let's do an animation of two wave fronts or two crests of a wave being emitted from the source. And remember, the distance between two wave crests is what we call lambda. So this is lambda, the wavelength of this particular wave. Now, what if the source is now moving towards the observer? This is what it looks like now. So we emit a wave crest here, and we emit another wave crest over here. But you see that the first wave crest is emitted at the center of this bigger circle. Okay, so it spreads out from here. But the second wave crest is emitted from this point at the center of the smaller circle, because again, the source has moved in the time it took to emit those two wave crests. So the idea is, as a result of that, if you think about the distance between the two wave crests that the observer is receiving over here, it's going to be a smaller wavelength than before. Lambda prime is smaller than lambda if the source is moving towards the observer. Now, how can we compare lambda and lambda prime? Well, we're going to use this fact. Again, the first wave crest, this bigger one, is emitted right here at the center of the big circle. The second one is emitted right here at the center of the smaller circle. And the distance between those 2 points is basically just the speed that the source is moving with times the time. So the speed is v source, that's what we'll call it. And the time is actually one period, because we're talking about the time between one wave crest being emitted and another wave crest being emitted. That's the period. So we can relate all of this. We can compare the wavelengths in the following way. So the shortened wavelength lambda prime is equal to the unshifted wavelength lambda minus v source times t. That's how we compare the two wavelengths. So next, we'll recall that the period is the inverse of the frequency. So t, that's the period over here, is just 1 divided by f. Okay, that's the period. Another thing we'll remember is that the speed of a wave is equal to lambda times f. And remember, the speed of the wave is the same in both cases, right? In both cases, these wave fronts are approaching the observer at the speed of sound. So what we can say is v sound, the speed of sound, is equal to lambda times f. So this wavelength times the frequency that this observer would be hearing. But that's also equal to lambda prime, which is this wavelength, times f prime, the frequency that this observer would be hearing. Now, we can put all of that together and make substitutions into the first equation. So let's take a look at a few things. Lambda prime, right? What's that equal to? Well, that's going to be the speed of sound divided by f prime, according to this equation. What about lambda? Well, that's going to be the speed of sound divided by f, again, according to that same equation. So if we make those substitutions, lambda prime is going to the speed of sound divided by f prime. That's on the left side of the equation. Lambda is going to the speed of sound divided by f. That's going here. And then we subtract v source times t, but that's going to be v source divided by f. Okay, so that's what we have so far. Okay, so let's take that result that we got by looking at those two different diagrams, and let's just manipulate it a little bit. So if we invert both sides of the equation, in other words, we flip the fraction on both sides of the equation, on the left side, we're going to have f prime divided by the speed of sound. And then on the right side, because f is in the denominator here in both terms, f goes to the top, and it divides out v sound minus v source. So the last thing we'll do here is simply multiply on both sides by v sound, and that tells us that f prime, that's the shifted frequency, is equal to f, that's the original frequency of the source. That's equal to f times v sound divided by v sound minus v source. So, just to be clear, this formula assumes that the observer is stationary and the source is moving towards the observer. So in general, if we have a moving source and a stationary observer, the source can be moving towards the observer or away from the observer. So the general formula for this sort of situation, where we have a moving source and a stationary observer, is to say that instead of a negative sign being on the bottom here, it can be negative or it can be positive. We know that it's negative if the source is moving towards the observer. That's the case we worked out. We know that sign is going to be positive if the source is moving away from the observer. Okay, so we have two possible signs depending on which way we're moving. Okay, so up until this point, we've derived a formula for the Doppler shift when you have the source of the sound moving and the observer is stationary. Now we want to look at the opposite case, where the source is stationary and the observer is moving. Okay, so we're going to compare two different diagrams like before. In case number one, they're both stationary, so the source and the observer are both stationary. And this is what we saw before. We emit a couple wavefronts, and the distance between neighboring wavefronts is equal to lambda. Now, in the second case, we're going to watch the observer moving towards the source while the source is emitting some sound. So the speed of the observer is v observer. And this is what it looks like. We emit one wavefront and then another. And notice how the wavelength actually doesn't change. In other words, lambda, in this case, is the same as lambda prime. That's the first thing to notice about this case. So lambda is equal to lambda prime. That actually hasn't changed. But what has changed is the speed. Okay, so in this first case, the observer is going to see these wave fronts coming at him at the speed of sound. In the second case, the observer is going to see the wave fronts coming at him even faster than that. So in other words, let's call v prime the speed that the observer sees the wave fronts coming at him. That's going to be v sound plus v observer. We have to add those two speeds together because we have to take into account the motion of the observer. Now, remember, there's a fundamental relationship between wavelength and frequency and the speed of a wave, which is v equals lambda f, right? Well, if v is equal to lambda f, that means lambda is equal to v divided by f, okay? And so this is what we're going to use. Since lambda and lambda prime are the same, we can set them equal to each other, okay? So let's do that. Lambda is equal to lambda prime. And then each one of those is the speed divided by the frequency. But in the first case, we have v divided by f. And in the second case, we have v prime divided by f prime. Okay, so v divided by f, we're talking about the speed of sound divided by the unshifted frequency f. In the second case, for v prime, remember that's the speed of sound plus the speed of the observer divided by f prime. And so now we can rearrange this equation to solve for f prime. F prime, if you solve for it, is going to be equal to f times v sound plus v observer divided by v sound. And that's how we get the Doppler shift when you have the observer moving towards the source, which the source is stationary. But of course, the observer could be moving away also. So in general, if we have a stationary source and a moving observer, this is the formula. F prime is going to be equal to F times the speed of sound plus or minus the speed of the observer divided by the speed of sound. So we're going to use the plus sign in the case where the observer is moving towards the source. That's the one we did in our derivation. You would do the negative sign if the observer is moving away from the source, okay? Okay, so we have two results that we've derived so far, and what I want to do is combine them into one. So the first is if we have a stationary observer and a moving source, that was the first result we derived. We get f prime is equal to f times v sound divided by v sound minus or plus v source. And in the case where we have a stationary source with a moving observer, then we have f prime equals f times v sound plus or minus v observer divided by v sound. So in general, if we have both a moving source and a moving observer, which is the general case, then we'll have to sort of combine these two results. And this is the idea behind that. F prime is going to equal f times the first factor, which is v sound, divided by v sound minus or plus v source. And then we multiply by the second factor, which is v sound plus or minus v observer, divided by v sound. So we can cancel v sound here and here. And the general result that works in every case is that f prime is equal to f times v sound plus or minus v observer divided by v sound minus or plus v source. So this is the general case. Okay, so what we've shown is that you can combine the two results that we derived previously to get something that is valid in general. In other words, when the source and the observer are both moving relative to the air. So here is the Doppler shift in general. We have f prime, that's the shifted frequency, is equal to f times the speed of sound plus or minus the speed of the observer divided by the speed of sound minus or plus the speed of the source. Now, we have to be clear about how to determine the signs, because in the numerator, we have our top sign as plus and our bottom sign is minus. And down here in the denominator, the top sign is minus and the bottom sign is plus. So the rule is this: you're going to use the top sign whenever you have something moving towards something else, and you're going to use the bottom sign when you have something moving away. So that's how you determine the sign. Okay, so there's just one little bit of complication on top of what I said, which is that in our derivations, we assumed that the source is moving directly towards the observer and the observer is moving directly towards the source, that kind of thing. In general, you don't have to be moving directly towards the object emitting the sound. You could be moving in any given direction. So in general, when you see v observer and v source, you want to think of these as components of a velocity along the line of sight. So the line of sight is just what we call a line that connects the source to the observer. So in general, right, you can have an observer over here and a source over here. The line of sight is this line that connects the two. And the velocity of the source and the velocity of the observer, again, they don't have to be going right towards each other or directly away from each other. The velocity can be in any direction, okay? So what matters as far as the Doppler shift is concerned is just the component of the velocity along the line of sight. So v observer would just be this component right here, the velocity of the observer along the line of sight. V source would be this component over here, the velocity of the source along the line of sight. So in general, when you're not just dealing with one-dimensional motion where things are moving directly towards or directly away from each other, you have to keep this in mind, okay? So let's take a look at an example where we actually get to use this formula. So suppose the siren on a fire engine emits a sound with a frequency of 1,610 hertz. If you are stationary, you're standing here, and the fire engine is moving directly towards you at 45 meters per second, what frequency will you hear? And then as a follow-up, if the fire engine is moving directly away from you at 45 meters per second, what frequency will you hear? And then finally, if the fire engine is stationary and you are moving directly towards it at 45 meters per second, what frequency will you hear? So for this, we're going to need to know the speed of sound. So let's take the speed of sound in air to be 343 meters per second. So pause the video, try to work this out using the Doppler formula that we just derived, and then come back to the video when you think you have your answers. Okay, so a few things to just put down at the beginning. F is the unshifted frequency, which is 1,610 hertz. So unshifted. We want to know F prime in each one of these scenarios. So the shifted frequency. Now, the general formula is F prime equals F times V sound plus or minus V observer divided by V sound minus or plus V source. Okay, so in the first example where we have the fire engine moving towards you, so fire engine moving towards stationary you, well, the speed of the observer is going to be 0 because you're not moving. And the speed of the source is going to be the speed of the fire engine Since it's moving directly towards you, we can just use 45 meters per second. And given that it's moving towards you, we should use the top sign, okay, in the Doppler formula. So we have f prime equals f. Then we take the speed of sound, which is 343 meters per second. Actually, here, let me go back a second. F has a value that's 1,610 hertz, so we'll plug that in for f. And then for v sound, we have 343 meters per second, plus 0 because the observer is not moving in this case. And then we have 343 meters per second on the bottom for the speed of sound. And then we're going to use the top sign, which is minus, and then v source is 45 meters per second. If you crunch these numbers, you're going to get 1,850 hertz. So it's what you expect. You hear a higher frequency when the fire engine is moving towards you. Okay, so in the other example, in the next example, we have the fire engine moving away from you, and you are stationary, so away from stationary you. Again, you're the observer of the sound, so you're not moving. V observer is equal to 0. And just like before, V source is equal to 45 meters per second, but now it's moving away from you, which means we use the bottom sign in the formula. So f prime is equal to f, 1,610 hertz, times the speed of sound, 343 meters per second, plus 0, because again, the observer is not moving, divided by 343 meters per second, and then the bottom sign is plus in the formula. So we have plus 45 meters per second in the denominator here. If you crunch these numbers, you're going to get 1,420 hertz. Again, that's what you expect when the source of the sound is moving away from you. The frequency is pitched downwards. It's shifted downwards. So the last case that we want to look at is you are moving towards the stationary fire engine. So you might guess, well, wouldn't it just come out to 1,850 hertz like the first example we did? The answer is actually no. It's going to come out slightly differently. Because now we have V source equals 0. Now the source of the sound, the fire engine, is equal to 0. And now the observer, that's you, are moving at 45 meters per second. And since you're moving towards the fire engine, we better use the top sign in the formula. Okay, so now f prime, go back to the formula, is equal to f. So that's 1,610 hertz. And then we have the speed of sound, 343 meters per second. And then plus or minus the speed of the observer on top. So we're going to use the top sign, which is plus, and the speed of the observer is 45 meters per second. And then we're going to divide by 343 meters per second, and then we have minus or plus the speed of the source, but that's just 0. The source is not moving in this case. So if you make this calculation, you're going to find it's 1,820 hertz, which again, it's not exactly the same situation as the fire engine approaching you. It's a different Doppler shift. Okay, so here's an example for you guys to work on. We have a model airplane that's being flown in a counterclockwise circular path at a constant speed. Alice is standing at the center of that circular path, and Bob is standing outside of that circle, as we see in the diagram. So Alice is standing right here in the middle of the circle. The plane is being flown in a circle going counterclockwise like this, and the speed is going to remain the same. And Bob is standing outside of that circle over here somewhere. The engine of the plane creates a buzzing sound that has a certain characteristic frequency to it. So for the locations of the airplane shown on the diagram, so when the airplane is here at point 1, here at point 2, and here at point 3, what does each person observe? Did they observe an increased frequency, a decreased frequency, or an unchanged frequency? So pause the video, try to work this out, and then we'll go through it together. Okay, so we'll start by writing down some general things we know. F prime is equal to F times V sound plus or minus V observer divided by V sound minus or plus V source. And again, we use the top sign when it comes to motion towards and the bottom sign for away. So if we apply this formula to Alice, so if we say Alice is the observer, well, she's not moving. So Alice is not moving relative to the air, so V observer is equal to 0. What about V source? So the plane is the source of the sound. And notice something about V source. Okay, we have the line of sight, I'll write this as LOS, between Alice and where the plane is. Let's say the plane is over here. That's point P. The plane is always going to be moving tangent to the circle, which means that the velocity is always going to be at a right angle relative to the line of sight. In other words, the plane is always moving perpendicular to the line of sight. LOS. And that means V source is just equal to 0, right? If you think about it, the plane is never moving towards or away from Alice at all. It's just keeping the same distance away from Alice as it moves. So therefore, F prime is going to be equal to F V sound plus 0 divided by V sound plus 0, which is just another way of saying that F prime is equal to F. Alice hears an unshifted frequency at every point. So it doesn't matter if we're talking about point A, point 1, point 2, or point 3. Alice hears an unshifted frequency at all of those points. Okay, when it comes to Bob, this is a different story. So Bob is now the observer. Bob is not moving relative to the air, so V observer is equal to 0. But we can't simply say that V source is equal to 0 in this case. So if we look at point 1, so imagine the plane is over here at point 1. Remember, it's moving in a counterclockwise circle. So at point 1, the velocity of the plane is going to be straight down, actually. And the line of sight connecting Bob to the plane would be this. And V source would be this component of the velocity along that line of sight. So that's clearly not going to be 0. Since the source, that's the plane, moves towards the observer, okay, that's going to be Bob. We're going to be using the top sign in the formula. So here's what we have. F prime is equal to f, v sound plus 0 because the observer is not moving, divided by v sound, and then we use the top sign, which is negative v sound minus v source. And so this is going to end up being an increased frequency. So f prime is bigger than f in this case because what's in the denominator is smaller than what's in the numerator up here. So that's going to be f prime bigger than f in this case. Now at point 2, now the plane is going to be moving straight to the right like this. So the velocity of the plane at point 2 is going to be moving to the right. And the line of sight is this right here. So notice how now the plane is moving perpendicular to the line of sight. And that means the source, the velocity along the line of sight, is equal to 0. Okay, so for that moment, the plane is actually not moving towards or away from Bob. It's just moving perpendicular to Bob. So v source is equal to 0. And in that case, as we saw earlier, if v observer and v source are both equal to 0, we just get f equals f prime unshifted. Okay, and then the third case is the plane is over here at point 3. So now it's going to be moving straight up like this. That's the velocity vector. And basically, it's moving away from Bob. That's what we want to see here. At point 3, the plane source moves away from observer. So what does that mean? We're going to use the bottom sign. So f prime is going to be f times v sound plus 0 because the observer is not moving, divided by v sound plus v source. Again, in the formula, we're using the bottom sign right here, which is plus. Okay, so the numerator is now smaller than the denominator, which means f prime is less than f. So we're shifted down. Okay, so to summarize, for Alice, always unshifted. So she's not hearing any different of a frequency than what's being emitted. F prime is just equal to f. For Bob, at point 1, the frequency is shifted up, so higher frequency. At point 2, Bob's hearing an unshifted frequency. And then at point 3, Bob is hearing a lower frequency, shifted down. Okay, so that's how this works. Okay, let's do another Doppler shift example. So bats are capable of emitting sound waves into their environment that reflect off of nearby objects. And then the bats can receive those reflected sound waves back. And when they do that, they can get information about what's out there in their environment. So it's kind of like seeing with sound waves, this ability to detect what's out there in the environment using sound waves is called echolocation. So let's suppose we have a bat that's flying directly towards a bug, which is stationary. So the bat is moving at a speed of 3.500 meters per second. The bat emits a sound wave that has a frequency of 5,000.0 hertz, which reflects off of the bat, and then it comes back to the bat. So what is the frequency of that reflected sound wave that the bat hears? We're going to assume that the speed of sound in air is 343.0 meters per second. So here's a hint. The Doppler shift formula needs to be applied twice. So once for the incoming wave, and again for the reflected wave. So let's work this out. Okay, so we'll start with the general formula for the Doppler shift. F prime is equal to F times V sound plus or minus V observer divided by V sound minus or plus V source. Okay, so as suggested, we're going to apply this formula twice. Once for the shift of the incoming wave. So let me show you what I mean by this. So we have a bat that is emitting some type of sound, and the bat is moving towards a bug at 3.5 meters per second. So here's the bug. So the bat is going to be the source of that incoming wave, and V source is 3.5 meters per second. Now, the bug is going to be the observer of that sound wave, and the bug is stationary, so V observer is equal to 0. And since we're talking about the source moving towards the observer, we're going to be using the top sign in our formula. Okay, so F prime is equal to F, which is 5,000 hertz. That's our unshifted frequency. The speed of sound is 343.0 meters per second. And then we have plus or minus V observer, where V observer is going to be 0, divided by the speed of sound, 343 meters per second once again. And then we're using the top sign, which is negative. And then V source is 3.500 meters per second, like that. Okay, if you calculate this, you're going to get 5,051.55 hertz. And 4 sig figs on that one. So that's the frequency that the bug is going to be receiving, okay? But what happens is the bug reflects that sound wave back towards the bat. So there's another shift happening of the reflected wave. Okay, so for the reflected wave, this is how we want to think about it. Now, the bug is emitting that reflected wave back towards the bat, who's again still moving towards the bug at 3.5 meters per second. And what do we have then? The observer of this reflected sound wave is going to be the bat, moving at 3.500 meters per second. And the source is going to be the bug, who's not moving at all. Okay, so for the reflected wave, again, the bug is the source, the bat is the observer. So just like before, I can find the shifted frequency, F prime. Now, the frequency that the bug is emitting is what we found earlier, which is 5,051.55 hertz, and 4 sig figs on that. Now that multiplies the speed of sound, 343.0 meters per second. And then our observer is moving, moving towards, so we're using the top sign. So here's what I'm talking about. We have the top sign being plus, and the speed of the observer is 3.5 meters per second, divided by the speed of sound, which is 343 meters per second once again, and then plus or minus the speed of the source, but that's just going to be 0. The source is not moving. Okay, so if you crunch those numbers, you're going to get 5,103.09 hertz, which we keep 4 sig figs on. So this would be 5,103 hertz. So the bat emits a sound at 5,000 hertz, but it receives a reflected wave back at 5,103 hertz. Okay, so the fact that the frequency is shifted is something that the bat can use to get information about what's out there in its environment and how fast it's moving. Okay, let's do another example. We have two cars that are in danger of colliding as shown in the diagram. So we have a gray car, which is moving at 27.5 meters per second to the right. And then we have a blue car, which is moving at 21.5 meters per second straight up, and they're both approaching this intersection right here. The driver of the blue car honks his horn, which has an unshifted frequency of 1,250 hertz. What frequency does the driver of the gray car observe? We're going to take the speed of sound to be 343 meters per second in the air. Okay, so the blue car is emitting a sound wave, and at the moment it emits that sound wave, it is 43.5 meters away from the intersection. When the gray car receives that sound wave, it is 135 meters away from the intersection. So we're going to need to know those distances in order to do this calculation. So let's figure it out. Okay, once again, we're using the Doppler shift formula for frequencies. F prime is equal to F times the speed of sound plus or minus the speed of the observer divided by the speed of sound minus or plus the speed of the source. Okay, in this case, the unshifted frequency F is 1,250 hertz. So that's the unshifted frequency. We also have the cars moving towards each other. Which means in both cases, we're going to use the top sign. Okay, now let's draw a diagram of what's going on here. We have the gray car over here, and that's the observer for this situation. And directly to the right of the gray car over here somewhere, we have the intersection. So this is where they're in danger of colliding with each other. The gray car is moving straight to the right like this. So let's call this VG for the velocity of the gray car. And then down here below the intersection, we have the blue car, which is the source. Okay, the blue car is moving straight up like this towards the intersection. So this is going to be VB for the velocity of the blue car. And finally, we can actually connect these two with a little dashed line, which we call the line of sight. So the line connecting the source and the observer is called the line of sight. Okay. Now remember, when it comes to the velocities, we only care about the component of each velocity along the line of sight. So for the velocity of the gray car, okay, if I put a little line down onto the line of sight that's perpendicular to it like this, then this would be the observer. That's the component of the gray car's velocity along the line of sight. And similarly, if I project VB onto the line of sight like this, then this will be V source. So the component of VB along the line of sight is V source. Okay, we have an angle here, alpha. I'll just call that angle alpha. We have another angle here, beta. And then we have a right angle over here. So we have a right triangle where we have a horizontal side like this, a vertical side like this, a right angle between them. Then we have the line of sight, which connects the two. And then we have alpha up here and beta down here. That's the triangle we have. Okay, well, this distance is 135 meters, the horizontal distance. Again, that's the distance between the gray car and the intersection. The vertical distance is 43.5 meters. That's the distance between the blue car and the intersection. And the long side here, the hypotenuse, is, well, it's the square root of 135 meters squared plus 43.5 meters squared. That's just the Pythagorean theorem to get the hypotenuse. Okay, well, if we go back to the picture on the right here, we'll see that V source is equal to VB, that's the velocity, or that's the speed of the blue car, times cosine of the angle beta. Okay, so that's what you get by looking at this triangle over here. V source is VB times cosine of the angle beta. And in fact, we can actually work out what that is, because cosine, remember, is adjacent over hypotenuse. So we have VB, the speed of the blue car. That's 21.5 meters per second. And then cosine beta, which again is adjacent over hypotenuse. So for beta, the adjacent side is 43.5 meters. And the hypotenuse is the square root of 135 squared plus 43.5 squared. Okay, so if I want to do VB cosine beta, I can get cosine beta using the triangle we drew. Okay, and that's equal to, if you work it out, 6.594 meters per second. So that's the blue car's velocity along the line of sight. That's V source. Okay, V observer, according to this triangle we drew here, is going to be VG, the speed of the gray car, times cosine of alpha. Okay, so alpha is this angle over here. And again, cosine is adjacent divided by hypotenuse. So the speed of the gray car is 27.5 meters per second. And then cosine alpha is the opposite side, the adjacent side, which is 135 meters for alpha, divided by the hypotenuse, which is again the square root of 135 meters squared plus 43.5 meters squared, which gives us 26.17 meters per second. So that's the observer's velocity along the line of sight. So now that we've worked that out, it's just plug and chug into the Doppler formula. We have F prime is equal to F. Unshifted frequency is 1,250 hertz. Then we have the speed of sound, 343 meters per second, plus or minus the observer. So we're going to use the top sign, remember? So we're going to use plus the observer 26.17 meters per second. And then we divide that by 343 meters per second. That's the speed of sound. And then minus or plus the source. We're going to use the top sign, which is minus. And we're going to have 6.594 meters per second for the source. And if you crunch these numbers, what you're going to get is 1,372 hertz. If we keep 3 sig figs on that, 1,370 hertz. So the frequency is shifted up, higher frequency than before, because the source and the observer are moving towards each other. But we had to use this idea of a line of sight velocity because they weren't moving directly towards each other, right? That's the trick behind this one. Okay, so the last thing I want to talk about in this lecture is shock waves. I want to give you a rough sense as to what this is all about. And you may have heard of the term sonic boom before. This pretty much means the same thing for our purposes. So shock waves, sonic booms, that's what we're talking about. And what we're dealing with here is an object that is emitting sound waves. So we have some kind of source of sound waves, but that source is moving through the air faster than the speed of sound. So what does that actually look like when the source of sound waves is moving through the air faster than the speed of sound? I'll show you an animation to give you a sense of what's going on here. So this is going to be our source. It's going to be moving to the right. And then as it moves, it's going to be emitting sound waves. So you'll see the wave fronts moving outwards from the source. And here's what we have. So you'll notice that the object is actually outrunning its own sound waves. It's outrunning the wave fronts that it's emitting outwards. And something kind of interesting happened there, okay? Play that again if you need to. But the basic idea is that we have a pileup of those wave fronts, okay? So we have a wave front emitted here, another one emitted here, another one emitted here, and so on. And along this line, which we'll call the crest of the shock wave, all of those different wave fronts are just piling up and constructively interfering. That means we're going to have a region of really, really intense pressure right along the crest of that shock wave. But out here, it's pretty much going to be normal air pressure. So think about it. If you're standing here, it's just normal air pressure until all of a sudden the crest of that shock wave hits you, and all of a sudden the pressure is really, really high. It's really, really intense. And that's what it is like when you're hit with a shock wave. Okay, you have this sudden increase in pressure once you're hit with that shock wave. And again, what causes this is a source that is moving through the medium faster than the speed of sound in that medium. If that's the case, again, we have the source outrunning its own sound waves. That's what creates the shock wave. Okay, that's what this is about. There's a whole lot more you could say about that, but all I wanted to do is give you sort of a rough sense. So what we'll do is end the lecture here. As usual, we have practice problems at the end of this lecture that you can work on at home as you study for the test to do for practice. So that's it for this video. I'll see you in the next one. Until then, be safe out there, be healthy, take care.